Welcome! In this video I will show you how to normalize the radial wave functions. So this will be, I will be covering problem 4.11 as it appears in the third edition of Griffiths' Introduction to Quantum Mechanics. This problem states the following. It says part A, normalize R20 and construct the wave function psi200. And then B, normalize R21 and construct with the wave functions for 211, 210, and 21 minus 1. So what we will do is we will just take the radial wave functions. We are not supposed to calculate them this time. We did that in the previous video. So if you don't know where they come from, I do recommend you go back in the playlist and watch that video because it is good to know how you can calculate these. So we want to normalize them. And how do we normalize it? Well, we integrate over the entirety of space and we want that to be 0, right? So this would be integral from 0 to infinity of the radial wave function squared, r squared dr, right? We are integrating in spherical coordinates. In principle, this here would be multiplied also by the spherical harmonics, right? Which also have to be normalized, but they go in the, not from 0 to infinity, but they go from 0 to pi over 2 and 0 to pi, depending on whether you are in theta or phi, right? And you have to multiply here by sine. So the reason we have this r squared, of course, is because in principle, what we want to be normalized or should be the entire wave function, right? The entire wave function should be normalized, but we then separate it into these two integrals and they each have to be normalized separately so that the product is also normalized, right? If this integral is 1 and this integral is 1, then the entire integral is also 1. So that's just a quick explanation why we have this r squared there. Okay, so with that, let's begin because we simply have to plug it in. So in part A, we plug in R20. So 1 is supposed to be the integral from 0 to infinity of A0 over 2A, 1 minus R over 2A, e to the minus R over 2A, and all of this squared, right? And of course, we still have this R squared from there. So we still have to square this thing. So this thing has to be squared. So let's just square it right away. We get r over a here. Then we have this polynomial squared. And then we have a0 over 2a squared. Okay, so this gives us 1 is equal to a0 squared over 4a squared. And then integral from 0 to infinity of 1 minus r over a plus r squared over 4a squared. And we can actually multiply this by this r squared as well. So I guess I'm going to do that. So this is r to the fourth, r cubed, and this is r squared. And then we still have e to the minus r over a. So this now is a very, very common integral, and you should know how to solve this. Well, in fact, these are 3 different integrals. So this is a0 squared for a squared, and then we have integral from 0 to infinity of r squared e to the minus r over a dr. Then we have minus 1 over a integral from 0 to infinity of r cubed e to the minus r over a dr. And then we have plus 1 over 4a squared. And then we have, let's see. So this would be integral from 0 to infinity of r to the fourth e to the minus r over a dr. So these integrals are all of the same form. They are of the form, They are of the form integral is equal to 0 to infinity of r to the n, and then we have e to the minus, and then we have r, whoops, that's supposed to be r over, I don't know, b or something. All right, so they are all of this form. So how do we solve an integral like this? I'm going to show you the general case because I don't want to have to do this 3 times. So what we do here is we integrate by parts. So first of all, we are going to use substitution to turn this into just like u, for example. So to solve this, we can use a substitution. I like to use z. and we substitute for the thing that is inside of the exponent without the minus sign. And then we get dz, which is dr over b. So we can just plug it in. So we get integral, the limits have not changed. And instead of r, we have b times z. So b times z to the n, and then we get e to the minus z, and instead of dr, we have b dz. So what we get here is b to the n plus 1 integral from 0 to infinity of z to the n e to the minus z dz. So here we now just have to use integration by parts a few times, in fact n times. So what we will get is u is z to the n, du is n times z, n minus 1 dz. And then dv is going to be e to the minus z dz, and v is going to be e to the minus z with a minus sign. So this means that the integral is going to be, right, the product of these two parts, z to the n with a minus sign, e to the minus z, evaluated between 0 and infinity. And the beauty here is that this part will be 0 at both ends. So this thing is 0. And then we have minus the integral of the product of these two. But there's another minus here, so we get plus integral from 0 to infinity of n times z n minus 1 e to the minus z dz. So what we get basically is, right, if we call this I of n, right, this gives us n times I of n minus 1. Right? Each time we integrate, we simply lower the exponent, and then we go to the next exponent. So if we start at 5, we multiply by 5, and then we have to integrate again for the 4. So this means that we get n times n minus 1, so n minus 1 times I, n minus 2 in the next case. And if we do it again, n times n minus 1, I, n minus 3. Sorry, I missed multiplying by n minus 2, I of n minus 3. So we go like this all the way until we reach 1, right? Until we only integrate e to the minus z, right? The base case is going to be when we run out, right? I0, maybe let's call it. And that's going to be integral from 0 to infinity of e to the minus z dz, which is easy to integrate. This is simply minus e to the minus z between 0 and infinity. And this at infinity is 0. At 0, it is minus 1. So we get, or rather 1, but you have a minus sign in front, right? It's minus 0 minus 1. So this is simply 1. So this thing is simply n factorial. That is the point. This integral is simply n factorial, and you still have to consider, right? This is the result from this integral. So the result is b to the n plus 1 times n factorial. So that is what I wanted to show you, because now we're going to use this. Whoops, I meant to delete this. Okay. So this is what I just wanted to show you real quick. And now we're going to use it. So 1 has to be equal to a0 squared 4a squared. Now, here n is equal to 2. And b is simply a. So we get b cubed times 2 factorial, so simply 2. But sorry, b cubed in this case is a, so a cubed. A cubed times 2. Then we have minus 1 over a. Now n is 3, so we are going to get 3 factorial and also b cubed. And again, b is simply a, so a cubed. Okay. Is it, sorry, it's not a cubed, it's rather 3 plus 1, right? A to the 4th, because it's b to the n plus 1, right? Then in the next case, we have 1 over 4a squared times, and now b to the n plus 1, n is 4, so we get a to the 5th times 4 factorial. Okay, so as you can see, that was a pretty nice way of sparing us the pain of having to integrate. So from here, we get 1 is equal to a0 squared. Let's see. So this thing here gives us a cubed. this thing here also gives us a cubed, so we can factor it out and cancel it with this a squared. So we get a0 squared, a divided by 4, and then we have 2 minus 3, and then plus 3, right? Because this is 4 factorial divided by 4, that's 3 factorial, which is that's actually 6. So let's be very careful. Yes. So this here is 3 factorial, so that's 3 times 2, and this is 3 times 2. So the result is the same because I had made the same mistake here, and it canceled out. But yeah. So this and this cancels out. So we get that 1 is equal to a0 squared a over 2, which means that a0 squared is equal to 2 over a, or simply that a0 is the square root of 2 over a. Okay, so that is our normalization constant. And what else? So we normalized it, and now we want to construct the wave function 2, 0, 0. Okay, so to construct the wave function, we keep in mind that our wave function is going to be the radial part, which depends on r, and the spherical harmonics, right, which depend on theta and phi. And of course, this is n, l, m. R, as we saw, depends on n and l, and the spherical harmonics depend on l and m. Okay, so to build this one, so to build 2, 0, 0, we take r to 0, which is what we already have, and then we add y 0, 0. So we have already calculated the spherical harmonics in the videos where we dedicated ourselves to studying the spherical harmonics. So I will not really calculate it again. That's why I included this table here. If you don't know how to calculate it, then you should go back and study that video, because you have to know that. And I went in depth, so it doesn't really make much sense for me to do it again in another video. So let's just plug it in. R20 is a0, which we know is square root of 2 over a. And then we have 1 over 2a, 1 minus r over 2a, e to the minus r over 2a. And now we multiply by y0, 0, which is the square root of 1 over 4 pi. Right? I'm just looking at this. So with this, let's see, we can perhaps simplify a few things, perhaps in the square root. Let's see. So I'm just going to write it right here. So this would be square root of 1 over 2 pi a, right? And then we have, well, I guess that's all we can really simplify. So then we have 1 over 2a, 1 minus r over 2a, e to the minus r over 2a. So there we go. That is the wave function 2, 0, 0. Let's go for part B. Here we want to normalize R21 and then construct the 3 possible wave functions. So we'll do the same procedure, right? 1 is equal to the integral from 0 to infinity of r squared. Now r squared, we can see right here, is a0 squared, 4 squared, a squared squared, so a to the 4th, r squared e to the minus r over 2a squared, so we get over a, and then r squared dr, again, this r squared coming from there. So that means that we get r to the 4th, combining these two. So let's take all of our constants outside. So we get a0 squared, 16, so that's a 16, a to the 4th. And then we have to integrate from 0 to infinity of r to the 4th, e to the minus r over a dr. Now we know what this integral is. We already solved integrals of this kind. Again, the result for integrals like this, right, when you have an integral which is 0 to infinity of r to the n, e to the minus r over b dr, this is simply n factorial b to the n plus 1. So in this case, we have, so let's put just the constants here, blah, blah. And then we have n equals 4, so we get times 4 factorial times b to the n plus 1, but b here is simply a. So we get a, and n is 4, so a to the 5th. So with this, we get that this would be a0 squared divided by, now 4 factorial is 4 times 3 times 2 times 1. So 4 times 2 is 8. So with that, this goes down to 2. So we have 2, and we still have a 3 up here. And then we still have a, right? Because this, the exponent here cancels out with that. So we have a squared, 4 times 2 cancelled out, 3 is still there. Okay, so this thing here has to be equal to 1. So that means that a0 is going to be 2 over 3a inside of our square root. So that is our normalization constant for R21. And with this, we can now just go ahead and construct our wave function. So let me just clear some space. We don't really need this anymore. We have already found our normalization constant, which I will now move to the side. There we go. Okay, so now let's construct this. So psi 2, 1, let's go for 2, 1, 1 first. So this would be R 2, 1. Now notice all of these will have the radial part 2, 1, right? Changing m does not change your radial function. So the R will be the same in all of them. So first we will take y, L equals 1, m equals 1. Theta, phi, whatever. So the radial part we already know, that's square root of 2 over 3a, that's a0, times 1 over 4a squared, r e to the minus r over 2a. And now we multiply by y11. So let's see. y11, right, the spherical harmonic here. If we are in the plus sign, then we need the minus in here and the plus over there. So this would mean y11, this means minus 3 over 8 pi to the 1/2 sine of theta e to the I phi. Is there anything we can really simplify here? A little bit, there is actually. So in the square root, this 3 cancels out with this. This turns this 8 into a 4. And by the way, I just saw the minus sign. I put it inside of the square root. I'm not supposed to do that. So that's kind of a blunder here. So let's just put it in front. Otherwise, that really is very bad. Okay, so this would be 1 over 4 pi a times r over 4a squared. And then we have, well, everything else. So then we have, I guess, sine of theta e to the minus r over 2a e to the I phi. So this is psi 2, 1, 1. Now, if we want to find psi of, so psi 2, 1 minus 1, well, the only difference is the minus sign, right? The minus sign in front, it used to be minus, now it's plus. And the plus sign in the exponential, it used to be plus, now it's minus. So all we need to do is take this result and write plus, so plus 1 over square root of 4 pi a. I guess you could take the 4 out of the square root if you wanted. I mean, it doesn't really matter that much, but you could do that. So r over 4a squared sine theta e to the minus r over 2a. So none of this has changed. And then e to the minus I phi. So that's the difference there. And then if we want to go for psi 2, 1, 0, well, we take the radial part again. So the radial part, it is a0, which is square root. So the square root of 2 over 3a. Then we multiply by 1 over, so 1 over 4a squared r e to the minus r over 2a. And I think that's it for the radial part. Yes, so now we go to y10, so this one right there. So 3 over 4 pi cosine theta. So 3 over 4 pi to the 1/2 cosine theta. Okay, so can we simplify anything? We can simplify a few things. So again, this with this 4 with this, it gives us a 2. So we get the square root of 1 over 2 pi a, and then 1, or rather r over 4a squared e to the minus r over 2a. and then just cosine theta, and there we go. So we found every single wave function here. You can see that this procedure is pretty simple. You could do this with any other one. Of course, the radial parts may be a bit more complicated, the polynomials may be bigger, but the procedure is the same. So if you could do this, then you can just build any wave function you need for the hydrogen atom. So yeah, I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in another video. Thank you very much for watching.